Let's take a look at bounded sequences and see if we can say anything about their subsequences. So it turns out, when we look at a bounded sequence, we can say that there always has to exist a subsequence that is convergent. So every single bounded sequence you have, the bounded sequence itself need not be convergent, but it does contain a subsequence that must be convergent. So let's see if we can prove this. So here, let's start with a sequence that is convergent, sorry, not that's convergent, that is bounded. So we have this bounded sequence. We can define S to be the set of terms that show up in that sequence. All right, so this set of terms, we wouldn't have, so this set S, it is not including the terms that are repeated more than once, so it's each term that shows up will show up in the set only a single time. And so we have a couple things that could be true about this set. Right? So case one, that set could be finite. Right? So we have in this set S, we only have a finite number of things. That doesn't mean that our sequence was finite to begin with. It just means that there is at least one value that shows up there in that sequence that showed up an infinite number of times. Right? And so that's really how we are going to build a subsequence that is going to converge. Right? So if S is finite, then there exists an X in this set S such that X is equal to S sub n for infinitely many choices of n. All right, so we have this value X that is equal to S sub n for infinitely many choices of S, for infinitely many choices of n. Right? Right. And that is to say that there exist these indices n1 less than n2 less than so we have these indices such that x, nope, not x, s sub n1 is equal to k, s sub n2 is equal to k, or is not equal to k, is equal to x. S sub nk is equal to x. Right? They just keep on going. Right? So if we think about this subsequence of our original sequence S sub n, so S sub n sub k, that subsequence is a subsequence that only consists of the terms x, 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 x. And so what does it converge to? Well, it has to converge to x. So when we have S is finite, if this setup here is a finite set, then we know for sure there has to be a subsequence that converges. What happens if that set is not finite? So if that set S is infinite, so we have this bounded set that is infinite, so then by the Bolzano-Weierstrass theorem, by the Bolzano-Weierstrass theorem, S has an accumulation point. Let's call that value y. And what our goal is going to be, what we're going to try to do, is we're going to try to construct a sequence that is going to, a subsequence of S sub n that's going to converge to this value of y. So, for each k in the natural numbers, we can let a sub k be this interval, so y minus 1 over k to y plus 1 over k. Now you might notice, so that is an interval, but it's this particular interval. It is a neighborhood. It's a neighborhood about y with radius 1 over k. And so we have this neighborhood about y with radius 1 over k. Because y is an accumulation point, given k in the natural numbers, there have to be infinitely many points or infinitely many values, I guess is maybe a better way to say, of n such that S sub n is an element of that neighborhood. So we have to have an infinitely many values. And so what we're going to do is we are going to choose values in each of these neighborhoods as our values of k change. Right? So that's our idea. Choose S sub 1 and A1. We could, and I shouldn't call that S sub 1, I should call that S sub n sub 1, because it need not be the same as the first term in the original sequence, so it could have a different index. Right, but we can choose an element that's in A1. And then after that, we can make sure that we have something that's further along in the original sequence. That also is going to satisfy, this is not only in A1, but it's actually in a slightly narrower neighborhood. And in general, we continue to do that, right? In general, choose S sub n sub k and A sub k such that n sub k is bigger than the previous index of the term that we chose for S sub n sub k minus 1. Right, and so we're moving along. Then what is true about this? This sequence is a subsequence of the original sequence. And it's a subsequence of the original sequence with the absolute value of s sub n sub k minus y is less than the radius, or that value of epsilon, which is 1 over k. But this is true for every choice of k that we could make, every natural number. And thus, this subsequence that we have built, it is going to be convergent to y. So regardless of whether or not this the number of terms in the original sequence was finite, or number of different terms in the original sequence was finite or infinite, if that original sequence was bounded, then there has to be a subsequence that is convergent. You might say, what if I have a sequence that is unbounded? That's a good question. And so we can say something about when we have an unbounded monotone sequence. Every single unbounded monotone sequence, it contains, let me back up. Every single unbounded sequence contains a monotone subsequence that has either positive infinity or negative infinity as its limit. Right? So whenever you have an unbounded sequence, there's always a sequence that is monotone, so it's either increasing or staying the same, or it's decreasing or staying the same, that has either positive or negative infinity as its limit. And we won't take the time to prove that here. You can prove that on your own. You can look at any standard text in real analysis, so in particular our textbook, or a textbook by David Lay. It has a proof there on page 189. Next time we'll talk about subsequential limits. All right, we'll talk to you guys later.